Welcome to the Bridge Project's academic video. We have a ton to talk about, so let's dive right into it. The first topic we're going to cover is the concept of force. Thanks to Sir Isaac Newton, we can describe force mathematically. His second law states that an object's net force is equal to its mass times its acceleration. Thankfully, bridges are still and not accelerating, which means that the net force has to be equal to 0. A big part of bridges is keeping the walkers, the drivers, even the trains that travel across them safe. A key to keeping everything safe is the balancing of those forces that we just talked about. Trusses actually play a very big part in the balancing of those forces. Instead of just having one member, as we call them, absorb all the load and likely breaking like this, trusses, like shown here, can interconnect many different members and form a very strong structure that does a great job of balancing those forces. So after looking and examining a few different trusses, you might start to see a little bit of a pattern, and that is that all trusses are made out of a bunch of different triangles. Believe it or not, triangles are actually the strongest shape in the world. Let me show you a quick demo about why that's the case. So right here is a parallelogram, and watch this. It's able to wiggle side to side because there's so many degrees of freedom and nothing's really stopping it. But watch what happens as soon as a cross member is introduced that turns it into two triangles. This parallelogram, now into two triangles, no longer has that ability to go side to side because those triangles are rigid and restrict all kinds of movement. Here's a triangle from the get-go, and as you can see, there's no movement that occurs. And why that is because the different members are not willing to change their length. If none of them are willing to change their length, they're not going to move at all. So nothing's willing to give, and that's why triangles are the strongest shape in the world. What is happening on your screen is actually the mathematical analysis of a truss structure. Please don't worry, we by no means expect you to learn this process. We just want to show you that it exists. Like I mentioned earlier, trusses take a load, which is essentially a collection of forces, and they distribute them among the different members so they can share that load. These analyses are not taught until about college engineering school. They can get pretty lengthy and complex, but they do end up telling us some useful information, like how much force each member absorbs, and whether or not it is in tension or compression. Valuable insights for design engineers. As you can see in the video of the analysis, it is the engineer's job to sum the forces in the X and Y directions and use information like the weight of the load and the dimensions of the members to solve for any unknowns in the structure. As I mentioned earlier, all the different members in the trusses are ideally in tension or compression, which brings us to our next topic of stress. No, I'm not talking about the type of stress that makes you want to pull your hair out, but the type of stress that takes force to the next level and bumps it up a notch, which I know you guys can handle. Its equation is stress equals force divided by area. Here's a brief demonstration that should help visualize that formula and help visualize stress and really showcase its importance in trusses and bridges. This is my little brother Luke. Watch what happens when I step on him with my very tippy toes, which is supposed to resemble a small surface area and kind of a high stress. Let's see if he feels it.
Ow, ow, ow.
But remember, trusses are designed to really distribute the weight of the bridge and even it out so members don't break, which is exactly what these textbooks are for. Watch what happens when I put these on Luke's back and step on him with this large surface area. I wonder if he'll feel anything. When I step on Luke with these textbooks, which really distributes the weight, I bet he doesn't feel a thing. How you doing down there, Luke? You feel anything?
Don't feel it at all.
I mentioned earlier that trusses are technically supposed to keep their different members in either tension or compression. But in reality, other types of stresses exist. And since our bridges aren't exactly perfectly and precisely made, that makes room for these other stresses to come into play in our bridges. A couple other forms of stresses are torsion and also bending. So although we're only focusing on truss bridges, why don't you check out and see if you could recognize some of these other types of bridges. So that way, when you see them in the real world, you're going to know what you're seeing, and you're going to be able to speak about them knowledgeably. Suspension bridges, like the Golden Gate or Brooklyn bridges, are very common and very beautiful. The key feature on them are the massive cables that are suspended between the towers and anchored at the end. Any load from the bridge gets transferred onto those cables in the form of tension. The numerous vertical cables are called hangers, which support the roadway and allow for travel across. Normally, 2 towers on the end will work, but for some large spanning bridges, a third may have to be introduced somewhere in the middle. Arch bridges are also fascinating to study. They are very popular in mountainous regions because no support is required underneath in hard-to-reach, steep locations. They work by transferring their loads in nearly 100% compression down and out through the bridge and into its supports and the ground. Although it is the main feature, engineers actually have to be careful not to make the arch underneath too big, or else, believe it or not, it will actually weaken the bridge. Finally, we have beam bridges. These are the simplest kind. Technically, a log over a creek could be considered a beam bridge. Although they are simple and cheap, they have tons of practical applications, like highways. They can only span so far, but luckily, we are able to stack a bunch of them together or add more beams to make them longer if need be.